Now, for the next part of your lesson, we go through something called Doppler shift. Doppler shift is actually Doppler effect that we've learned under AS physics waves. So we are just recapping what we've learned here. When you have a stationary wave source, the wave fronts from that wave source tend to spread out symmetrically or evenly. What we mean by that is if you look at the diagram here, you had a car that was stationary. You assume that the car is sounding its horn so that the sound waves produced by the horn is now spreading out in all directions in this manner. Okay, but because the car itself wasn't moving, the sound waves spread out symmetrically or evenly. But what happens when the car starts to move? What happens when the source of waves starts to move? The waves that are produced by the horn can become squashed together or stretched out. When the source is moving towards an observer, the wave fronts will actually appear squashed. But on the other hand, if the source is moving away from the observer, the wave fronts would appear stretched out. So you can actually see in the second diagram right over here, when the car is actually moving towards the right. So when the car is moving towards an observer, say right over here, you can see that the wave fronts are appearing to be squashed. But then if say you had another observer here and the car is moving away from the observer, you can see that the wave fronts appear stretched out. Okay, so what you can then say from here is that when you have a wave source that moves relative to an observer, there will be changes in the observed wavelength and hence frequency. Okay, so right now, if you have a moving object, it causes the wavelength lambda of the waves to change by delta lambda. When it comes to the source moving towards the observer where the waves are squashed together, the wavelength in front of the source decreases lambda minus delta lambda and frequency increases. And on the other hand, if the source is moving away from the observer where the waves are being stretched out, the wavelength behind the source increases lambda plus delta lambda and the frequency decreases. Recall that your wavelength has an inverse relationship with your frequency, such that if your wavelength drops, your frequency increase, and then if your wavelength increase, your frequency drops. Okay, now regardless of whether your source is moving towards the observer or away from the observer, bear in mind that the actual wavelength emitted by the source remains the same. It is only the wavelength received by the observer or perceived by the observer that appears to have changed. All right. So this effect is what you know as the Doppler effect or the Doppler shift, which can be defined as the apparent change in observed wavelength or frequency of radiation from a source due to relative motion between the source and the observer. Now, in AS waves, you normally related the Doppler effect to sound waves, but Doppler effect can also be exhibited by EM radiation, specifically EM radiation emitted by stars. The Doppler effect can be observed in electromagnetic radiation when comparing light spectrum produced from a close object such as our Sun with that of a distant galaxy. Now, as mentioned just now, in space, the Doppler effect of light or EM radiation can be observed from the emission or absorption line spectra of distant stars and galaxies. When it comes to the Doppler effect exhibited by stars or galaxies, you will see the term redshift and blue shift. Redshift means that the object is moving away from the Earth as the apparent wavelength is increasing towards the red end of the visible spectrum, whereas blue shift indicates that the object is moving towards the Earth as the apparent wavelength is decreasing towards the blue end of the visible spectrum. So to get a better idea of what the red shift and blue shift here means, let's relate it to your Doppler effect. So when it comes to Doppler effect, you could have source moving away from the observer. In this case, your observed frequency decreases, but your observed wavelength must be increasing because frequency and wavelength follow an inverse relationship. And then after that, when you have source moving towards your observed frequency is increasing, but your observed wavelength must be decreasing. So why are they called red and blue shift in the first place? It will be easily understood if you relate it to your visible light spectrum, Roy G. Beef. If you're going towards the right, where your wavelength is decreasing, notice that you're going towards the blue end of your visible spectrum. But on the other hand, if you're going in the opposite direction, where your wavelength is increasing, you're going towards the red end of your visible spectrum. That's why they're named red and blue shift respectively. All right. If you look at the two diagrams below, you will recognize this as the absorption spectrum of light. Okay, so the first diagram is actually produced from a close object such as the sun, whereas the second one is produced from a distant galaxy. So if you look at the missing dark lines here, those missing dark lines each represent a specific wavelength. For the first diagram, notice where the dark lines are. And then for the second diagram, notice where the dark lines are too. They are not at the same location. It seems as if the dark lines have shifted. They have changed location, they have changed their apparent wavelength. So this one will tell you that Doppler effect is actually happening. Okay, so when it comes to the Doppler effect exhibited by stars, usually they exhibit redshift rather than blue shift. So redshift here can be defined as the fractional increase in the wavelength or the decrease in the frequency due to the source and observer receding from each other. Receding here means moving away from each other. And there's a calculation that is associated with the Doppler redshift is given as delta lambda over lambda equals to delta frequency over frequency equals to V over C, where V is the speed of recession, the speed at which your source and observer are moving away from each other, and C is the speed of light in vacuum. Okay. Moving on to Hubble equation, which is related to redshift, in 1929, the astronomer Edwin Hubble observed that the absorption line spectra produced from the light of distant galaxies was shifted towards the red end of the spectrum. He observed many different galaxies and many different stars and observed that the majority of them displayed redshift. This redshift in the wavelength of light provided evidence that distant galaxies are moving away from the Earth. He also observed that light from more distant galaxies was shifted further towards the red end of the spectrum compared to closer galaxies. This means that the change in wavelength is actually more when he was looking at more distant galaxies. So here, he then concluded that galaxies or stars which are further away from the Earth are actually moving faster than galaxies which are closer, since the change in wavelength was actually more. So how does this relate to Doppler effect? We know that when source is moving away from the observer, the frequency drop and the wavelength increases. When source is moving towards observer, the frequency increase and the wavelength drops. So the frequency change and the wavelength change from Doppler effect actually depends on the relative speed between your source and your observer, where you can say something like this. If you have a higher relative speed between the source and your observer, your frequency change will be higher and your wavelength change will also be higher. Okay, so a higher relative speed between source and observer tends to result in a higher frequency change and a higher wavelength change. The change here could be an increase or decrease. We're talking about the magnitude of the change right now. So when it comes to light from more distant galaxies being shifted further towards the red end of the spectrum, this means that the change in wavelength is higher, which in turn means that the relative speed between the source and observer was actually higher. That's why Hubble concluded that galaxies that are further away from the Earth were actually moving faster, since the wavelength was increasing more. So if you look at the diagram below, this is the absorption line spectrum for different galaxies at different distances. The first diagram at the bottom is your laboratory reference, is the absorption line spectrum done at Earth. You notice the position of the black lines here. So Going further away from there, this one is showing you the light from distant galaxies. Okay, so the absorption line spectrum that you have here is for different galaxies with increasing distance. Notice the position of the lines now. They are not the same, indicating to you that there is actually Doppler shift. There's a change in wavelength here. So what you want to do now is to determine whether it is an increase or decrease in the wavelength. As I mentioned to you, it's always going to be redshift. So the wavelength is going to be an increase. But what you're interested to see here is the magnitude of the increase. Let's just focus our attention on the thick black line here. Okay, this one is our reference line. Okay, so when it comes to the light from the distant galaxies with increasing distance, notice the position of the thick black line. So you see for the nearby star, the thick black line has actually shifted by this much. This was the increase in your wavelength. But then after that, when it comes to the nearby galaxy, which is a bit further, the thick black line is now right over here. The magnitude of the increase in wavelength is actually more. And then when it goes to the distant galaxy right over here, the increase is even more. And then lastly, for a very distant galaxy, notice that the thick black line has shifted the furthest. You notice that as the distance was increasing, your change in your wavelength was actually increasing. This would have in turn meant that the speed at which your source is moving is actually higher. The relative speed between your source and your observer is actually higher. Okay. From here, Hubble related the distance between the star and the Earth and the speed with which the star is moving away from the Earth, where he stated that the speed is directly proportional to the distance. This is what we know as Hubble's law, where V is directly proportional to D. Hubble's law states that the recessional velocity v of a galaxy is proportional to its distance d from the Earth, which can be expressed as the equation v is equals to h naught d. If you remember just now I wrote that velocity is directly proportional to distance. You want to get rid of the proportionality sign, you have to introduce a constant, which in your case is h naught. So h naught is actually the Hubble constant. V is the recessional velocity of the object, the speed with which the object is moving away from your Earth, and D is the distance between the object and the Earth. So if you rearrange this equation here, your Hubble constant h naught is actually the ratio of your recessional speed divided by the distance. Okay. Now from the equation V equals to h naught d, if you were to compare the equation with the equation of a straight line y equals to mx plus c, where the y-axis is your velocity and your x-axis is your distance, if you were then to plot a graph of v versus d, the recessional velocity versus distance, you should get a straight line graph through the origin, which is what you're seeing on the diagram on the left. This is a graph of recessional velocity versus distance. You get a straight line graph that passes through the origin. Now, in order to validate that relation where you're supposed to get a straight line graph to the origin, actual measurements from stars or galaxies have actually been taken and they've been compiled together to see whether it follows the trend. So these black dots that you see all around your drawn line here are actually actual measurements done from distant stars and galaxies. So you'll notice that there's quite a bit of scatter about the line there. What you did was that you basically drew a best straight line fit. It's actually difficult to be certain about the accuracy of the values for the Hubble constant that you can deduce from the graph here due to the random and systematic errors involved when calculating the distance to a galaxy or star. Because you're talking about astronomical distances between your Earth and the galaxy and star, there are bound to be unknown factors. So that leads you to have some amount of random and systematic errors. Okay. In summary, as the universe is expanding due to stars and galaxies moving away from each other, with more distant objects moving away faster, this implies that matter must have been very close together or very dense in the past. Let's imagine that right now, everything else is moving away from the Earth. If you could stop time and rewind it a little, that means that everything else was closer towards the Earth. If you take this idea further and rewind time to the beginning of time itself, that would have meant that everything else started from one single point in the past. They were very close together or they were very dense. And then after that, when time started moving, everything started spreading out from there until today, and it's still expanding. This is actually the Big Bang Theory, which is used to explain the origins of the universe. It stated that the universe started from one single point in the past and started expanding from there, and is still expanding even now. Okay, so that should be it for this chapter. Let's do some questions.